you can start whenever.
Perfect. All right, check. Hey everyone, hello. Thanks for joining us today. It's a great pleasure to be welcoming and hosting Zac Manchester to U of T. He's been in Toronto once. This is his second time. All right, so Zac is an assistant professor in robotics at CMU. He used to be an assistant professor in aerospace engineering at Stanford, but he moved a couple of years ago. He did his undergrad in applied physics and his Ph.D. in aerospace engineering at Cornell. And later he did a postdoc at the Agile Robotics Lab at Harvard. After that he worked at NASA Ames and Analytical graphics. So I think the reason why you're here and what you're about to see in his talk is that Zac's research interests include motion planning, control, and numerical optimization with applications to robotic locomotion, spacecraft guidance, navigation, and control. And in general, Zac's work is known for its mathematical rigor and its modeling and optimization type of methodology. So as a result of that work, he won a number of major awards. One of them was the NASA Early Career Faculty Award in 2018, a Google Faculty Research Award in 2019, and most interestingly, he has also led 4 satellite missions, including one that is currently ongoing. So when we went for lunch, Zac was checking his email so that he can check with the student who was looking at the telemetry data from the satellites. And I think that's pretty much the first time we've had an invited speaker doing that over lunch. So without further ado, please give a warm welcome to Zac. Welcome,
Thanks so much for having me, guys. I guess just as ground rules, please yell at me and heckle me and interrupt me. It's way more fun if you guys are speaking up. Yeah, don't wait till the end. Just yell at me. Cool. So I guess the stuff I'm going to talk about is this deep rabbit hole I got started down as a postdoc, trying to think about how to reason about contact interactions on robots. And trying to wrap my head around that. And I guess 5 or 6 years later, I kind of landed at this made-up name for this stuff called, I call it composable optimization. So yeah, I guess as an intro to this, being as you mentioned, I'm a space nerd, lifelong space nerd. So this is one of my favorite robots, Mars Curiosity. And I guess a few stats on this, right? So this thing's been on Mars for 11 years. It's still operating. This is incredible. It's one of the harshest environments you can imagine, right? And in that time, it's driven 31 kilometers. This sounds like a lot, but if you divide those two numbers, that works out to about 7.5 meters per day, maybe 8 meters per day, which is not particularly impressive, right? Walking over there to the door is about what these things do in a day. And the reason for this, I've been fortunate enough to actually go visit this place, and it's super cool. Does anyone know what this is? So this is the famous Mars yard at JPL. It's basically a giant sandbox with a bunch of big rocks and stuff like this. And the way they drive the rover, there's basically a whole team of rover drivers. And when they get to a tricky spot on Mars with a big rock or whatever, a narrow passage, they basically take a bunch of imagery, and then they go out in the Mars yard with shovels and a backhoe, and they recreate the scene in this sandbox in Pasadena, and then they go and figure out how to drive the rover, and they practice a bunch of times until they get it just right, and then once they've gotten it just right, they uplink the commands to the rover, and it executes them. So as you can see, this is not a very autonomous, there has been amazing work, don't get me wrong, on autonomous driving for this kind of stuff, tremendous work out of JPL, but in a lot of cases, this is what's going on, right? It is, so put simply, it is not a very autonomous system, right? And there's still a ton of kind of human loop, motion planning and stuff going on. Yeah, so from there, from there, for me, so I'm now gonna kind of go through, there's a few parts to the talk. Part 1, I'm gonna try to convince you that almost everything, maybe everything is a bit of an overstatement, but almost everything we need be able to do this kind of stuff, to recreate the mountain goat with robots, at some level is optimization. So just a quick tour of things that are optimization. The first one that I'm sure everyone is well acquainted with is control. And whether it's model-based optimal control or RL or whatever, at the end of the day, all of these come down to some kind of optimization problem. I'm more of a model-based guy, so this is kind of the way I think typically, where you say, but this encompasses RL as well. So you have some model of your robot, right, that includes maybe your, it's either a learned model or your F equals MA kind of stuff, and then maybe some constraints that sort of define your actuator limits or this kind of thing, or safety. And then you write down some kind of objective function, cost function, reward function, whatever you want to call it, that basically encodes the behavior that you want, right? And then if things are relatively benign, you take this and you discretize it or whatever and throw it on your computer and you get an answer. You get a control policy, you get a trajectory, however you want to do that, right? So control, similarly, right, state estimation is an almost identical optimization problem. So figuring out where you are, pose estimation, all these kind of things, also optimization problems. And yeah, okay, that's whatever. Basically the same thing. This one is a little weirder, and one that, as a physics undergrad, I became acquainted with early on in life, but I think a lot of people in computer science are less acquainted with this idea. It turns out that physics is also, or can be, posed as an optimization problem. So anyone know what this thing is? This is Hamilton's principle. Who's heard of this? Okay, like maybe a handful, not too many. So Hamilton's principle is, this looks sort of suspiciously like that trajectory optimization problem or state estimation problem I just wrote down. It's almost the same. And what this says is that the trajectory that your system will follow, the trajectory that defined by physics, this pose trajectory, is the one that, so background, that's the pose, trajectory. This is the Lagrangian, so kinetic minus potential energy, for those who haven't seen a physics version of this before. The true trajectory followed by your system is the one that minimizes this loss function. This loss function is called the action, but it looks exactly like the kind of cost function that you would minimize in a state estimator or a control law, right? It's just integrated along the trajectory, blah, blah, blah. And it turns out, this is very uncommon, but there's no reason we can't solve this problem the same exact way we solve trajectory optimization problems. We can discretize this thing in time, and then directly minimize it on a computer. Why might I want to do this? Well, so A, this seems maybe expensive and weird, and why do I need this if I have my nice, ODE solver, Runga Kata method, whatever. And it is more expensive, but I think there's some pretty interesting things that you can do here. So if you take this perspective of this is just another optimization problem, one of the really cool things you can do is add constraints, just like we could add constraints in our motion planning problem. And in particular, the kind of constraints that we're interested in a lot in robotics are around contact interactions. So it turns out we're all maybe familiar a little bit with simulating systems that undergo contact interactions. It's terrible, right? You get soft contact models that are super stiff, or hard contact models that are non-differentiable. There's all this kind of crazy stuff. It turns out that if you just take this optimization kind of approach and double down on this Hamilton's principle, the true trajectory is the one that minimizes this cost function. Well, now I can just slap on any kind of constraints I want, and it's still a perfectly reasonable optimization problem, and we have good algorithms for solving these kind of constraint optimization problems. And so an example of this would be, say I have a brick, and this is kind of F equals MA stuff, and I want to simulate the brick, say, hitting the ground and sliding or whatever. All I've got to do is put an inequality constraint on there that says the brick is not allowed to go through the floor. So this would be a sign distance function that has to stay positive. And if I slap that on there and just minimize this problem, out comes impacts. And in all the kind of ways you would expect, basically, the Lagrange multiplier associated with that constraint becomes the normal force, all the usual stuff. And it just works. And you don't have to do any weird hacky things. It's stable, all the nice things. Similarly, if we want Coulomb friction, maybe some people have seen this before, this is called the maximum dissipation principle. A few people have seen this maybe. Same deal, it's an optimization problem. You get all this weird, nasty, non-differentiable stick-slip behavior with friction. Turns out it's just a solution to an inequality-constrained optimization problem. So if you're willing to kind of solve an SOCP at every time step, you get Coulomb friction, it's super clean, it works, you don't have to have creep in your simulator, it's very nice. Okay, and then the last one I'll mention is, this is kind of recentish work out of our lab. You can also pose collision detection as optimization. Classically, in a lot of simulators in the graphics community, there's algorithms like GJK, if people have heard of this, and typically the way these things work is you have a mesh and you kind of traverse the mesh in a very discrete kind of way. This works great, and there's very fast implementations of this. Where this isn't so nice is if you care about optimizing, taking gradients through that, for instance, those algorithms are not differentiable generally. So if you're instead kind of looking at, if you're willing to decompose all of the things you care about in your environment and your robot into a bunch of convex primitives, which is not crazy, that's actually what the GJK stuff does anyway, it just uses polytops or everything. So, you know, hills, boxes, whatever, this kind of stuff. So you get convex primitives. It turns out the collision detection problem can be written down as a convex optimization problem. It shouldn't be too kind of weird, you know, if you think you're basically looking for this closest point, it's a norm kind of thing with this convex. It's got to be, you know, kind of inside these two convex shapes, convex constraints. Hand wavy, it works out. You can check out the papers if you're curious. So that's out. So basically everything now in our simulation, state estimation, control stack, the whole thing, each one of these is an optimization problem. Hopefully this is like, you know, clear that we can do this. Okay, so if you will suspend your disbelief for a minute and trust me on that one. Then part two is, how do we put all these things together? So I just showed you, basically every single one of these blocks I can pose as an optimization problem. If now I say I want to put all that together and solve the, you know, say the big motion planning or control problem for a big robot that's the mountain goat robot, right? It needs to reason about the environment and the contacts and all of its dynamics and friction and geometry and all this stuff. If I have clean optimization formulations of each block, now I have this problem of when I go to solve the control problem, these are all coupled in really complex ways, right? So, so this is what I mean by composable optimization. How do I take all of these sort of separate problems and squish them together and somehow jointly solve them all in a reasonable way to get ultimately what I care about, which is my controller, out of this thing at the end, right? Okay, so that's what we're after. I now want to take a brief interlude for those who are like not so familiar with contact stuff and why it's a mess. So this is that like optimal control problem that we started out with, right? Cost function dynamics, whatever. And we're now going to think about it in the context of something like this, like a robot. The thing that's a mess here is, generally when we do this, we use either gradient-based or Newton-flavored, you know, first, second order optimization algorithms. In all cases, you're kind of implicitly assuming some degree of smoothness for all the functions in your problem. So the cost functions, we make those up, that's fine. Those can be whatever, we can make up nice, smooth, like quadratic costs or whatever. But the dynamics, we don't really get to pick, right? We're kind of stuck with that. In the case of stuff like this, when you have impacts and friction, the dynamics become non-smooth and non-differentiable. And if that's sitting in my F there and I need to take Jacobians of my dynamics, this causes huge, huge problems and basically breaks all of the standard optimization tools that we have, and kind of you need to do something. So there's a couple of ways people have dealt with this, you know, historically. The first one is so-called hybrid approach, and what we mean by this is if you're able to pre-specify the contact switching events, so basically when I touch down and lift off with my foot, say, I can sort of like bake that into the problem and then basically ignore it as far as the optimizer is concerned and only optimize over the smooth segments between impact events. This is great. It basically gets us back to the smooth problems we know how to solve, and there's great, you know, methods that can do this. The problem is I need some like oracle to hand me the contact mode sequence. There's all kinds of, you know, huge literature in the legged robot world about gate planners and all kinds of footstep planning heuristics. So cool, you can do this. There's lots of ways to do it. But at the end of the day, it ends up being pretty ad hoc and heuristic. And not only that, it ends up blowing up with, on you for problems that are what we call contact rich, where maybe it's not just point feet, but let's say you need to, I don't know, like, you know, reason about rough terrain. You need to, say, open a car door and sit in a car seat, and you now not just your feet, but the hands, all the different finger contacts, the rest of the body. As soon as you start having to reason about more potential contact points, the sort of contact planning problem ends up blowing up combinatorially and becomes really messy and hard to solve. Okay, so that's that. That said, these hybrid methods, right, have been hugely successful, most notably like this stuff that everyone's seen before, right? So roughly speaking, you know, from what we know publicly and, you know, from friends, like this, what these guys are doing is solving a big nonlinear model predictive control problem with a bunch of those kind of footstep planning heuristics and doing exactly this hybrid thing. So it can work extremely well, right? This is the state of the art, this is amazing. That said, you know, we've probably also seen some of these blooper reels, right? And if you look really carefully at this stuff, what you'll note is that most of the failure cases, especially look here, are due to unplanned contact events. So in that case, you know, it's trying to jump over, and its contact planner has, oh yeah, use your hand, but where it grazed its foot, that was an unplanned contact event. And in this kind of hybrid approach, one way of thinking about it is the controller is essentially running open loop on the contact modes. So if your planner says your hand's in contact and your feet are in the air, that's all it knows about. If during that maneuver, some other part of the body hits something in the environment, the controller cannot reason about it. It does not have that in the model. And so it just kind of barfs. And so in practice, the way you deal with this is by having all kinds of contingency plans, all kinds of like, oh, well, this other mode might happen, and you try to run these in parallel, or, you know, there's kind of, but it quickly becomes this combinatorial mess, right, to deal with these pre-planned contact calls. Okay, so yeah, can be awesome, but has some shortcomings, right, to do this hybrid thing. The other way to go, which is what we're now going to kind of get into and what has been my obsession for several years, is this so-called contact implicit approach. And this is kind of the dream. The idea here is instead of, you know, having these pre-planned contact modes and effectively just optimizing over the states and controls, you also want to reason over the contact forces and all of these potential contact interactions. So there's been some work on this over, say, the last decade or so. We've done a bunch of stuff on this. The dream here is that you can, you know, generate complex contact-rich gates, manipulation, kind of trajectories, all kinds of stuff. But I would say so far, like the issue here is fundamentally comes down to dealing with those non-differentiable contact interactions, and there's just severe numerical issues with this. And so trying to figure out a way that to formulate this problem in such a way that you can tractably optimize through these contacts is kind of the key thing here. Okay, so that's what we're trying to do. That's sort of the framing and context for this. And now we're kind of going to dig into this idea of composable optimization. So again, each one of these is a nice clean optimization problem that I know how to write down and in principle on its own know how to solve. So you know, this one's, and in fact, a lot of these are convex on their own, right? So this has a nice second order cone program. The like nominal robot dynamics, it turns out, is also like at least locally convex and pretty. The collision problem we just showed you is also convex, right? So all these things are relatively nice on their own. And we know how to do them in isolation, but how do we put them all together? Okay, so here's how we're going to do it. Just kind of getting into it. The key idea here is, so we're going to now zoom in on one of those blocks. And just in a very generic way, I'm going to write it like this. So we have an objective function, and for simplicity right now, we're going to just focus on inequality constraints, which are the impacts and things like that, right? So we'll ignore everything else just for clarity. Okay, so I have this problem. The first thing I'm going to do is I'm going to write down an interior point method to solve this problem. Who's seen this stuff before? A couple people. So the idea with an interior point method is I take those inequality constraints and I basically stuff them inside a function called a barrier function that blows up at the boundary of the constraint. And I stuff that into the objective function. So if I'll draw the picture in a sec. So I'm going to take the constraint and just stuff it inside this log. And the reason this works is the log blows up as you approach the constraint boundary. So as long as I start with a feasible point inside the constraint set, this thing is going to move the constraints now just into the objective. It's also, though, going to take that inequality constraint and effectively smooth it out. And you'll get something like this that's differentiable, globally differentiable now, right, as long as I'm in the feasible region. And then I also get this little parameter up front of the log, which is kind of this fudge factor thing, that I can use to tune the degree of smoothing. And in the limit, this curve kind of approaches the brick wall and gives you the exact answer to this problem. That thing's called the central path parameter, usually in the optimization literature, and it turns out there's all kinds of, there's like decades of theory on these things for how to make them, how to choose row effectively. And the punchline is that, we know how to solve these problems extremely well. With Newton's method, you can get quadratic convergence on these things. It's like, you can get answers to machine precision, it's great. Cool, so that's an interior point method. The trick that we're going to play now is we're actually going to take advantage of these kind of smoothing effect from the log, which is at the end of the day why interior point methods work to begin with. They work because they smooth this thing out, and now Newton's method works. I can take gradients and Hessians of this thing and do good numerical optimization. So we're going to kind of embrace that. We're going to take this sort of log barrier version of the problem, and we're going to solve it, but then we're going to leave this row kind of at some reasonable value so that this thing's nice and smooth. And based on that, I can now differentiate this problem as a solution. So the idea here is I'm minimizing over X. So to put this in context, right? Let's say I've got my physics, and I've got the robot dynamics with the impacts, and then I've got my Coulomb friction problem, that maximum dissipation problem. So these are two problems. In the robot dynamics problem, I'm optimizing over the pose trajectory, but it depends on the friction force, right? So in this case, in the robot dynamics problem, like X might be my pose trajectory, and Y might be is an external input to the problem. So it's a parameter of this problem, but it's not a decision variable. I'm not minimizing with respect to Y here. So physics problem, optimizing over pose, but like friction's an input. The friction problem, on the other hand, I'm solving for the friction. That's the optimization variable. But the pose trajectory is a parameter. It depends on the pose, right? So that's kind of the idea. Ultimately, what I want to do is hook those things together. Part of that is being able to get gradients of all of these blocks, right? So the way we do that is we kind of leverage that log barrier formulation. I solve this thing to convergence, and in particular, this R over here, these are the optimality conditions. So there's the KKT conditions for that problem, like the first order optimality conditions. So you haven't seen this before. It's basically the gradient equals 0 condition for an optimum, right? So I take those, and if I have those things, which I need anyway to solve the problem, I can diff through the solutions here to get the derivatives of the x's, the things I'm optimizing with respect to the y's, the parameters. So in this case, right, maybe this is, I can get the derivatives of my pose trajectory with respect to the friction stuff in this that matters in this other problem. So this is kind of how we're going to couple this stuff. This is called the implicit function theorem. Probably a bunch of you guys have seen this. That's what it looks like. But at the end of the day, what this lets me do is effectively get x as a function of y, and then dx dy here. Okay? Okay, so that's sort of how I get gradients of all this mess. The next key idea is what I borrowed this terminology from like the finite element CFD community. And I'll call this like strong versus weak coupling. So you can imagine if I have all these blocks and maybe I write down an optimization solver for each block, I can go solve each block on its own to convergence and then take a gradient of that block and treat that block as like some constraint in the other block, just a function that I can query. I can query the function value and I can query its gradient. And I could hook these all together and somehow, solve this one, then take its gradient, and then plug it into this one, and then solve this one. That is called weak coupling in other contexts. So we're going to embrace that terminology here. So weak coupling equals, I treat these blocks all as independent functions. I treat function evaluation as like solving the problem, and then I get the gradient, right? And that's, I think, how this is done in a lot of other contexts. Like, if you're familiar with like the convex layers kind of ideas in deep learning, it's basically what they do. They solve the problem, take the gradient, right? So it turns out, in our case, that does not work well. And instead, we're going to embrace this idea called strong coupling. So the idea here is rather than solve each of these and take their gradient and plug it into the other one, I'm actually going to take the optimality conditions for each block. Right? So this is the KKT conditions for this guy. It's basically gradient with respect to x equals 0 for all that stuff, and the constraint stuff, and the multipliers, whatever, all that garbage. It's a function of both x and y. So I get one set of optimality conditions here, and then this other one, which is the other problem, say the friction problem, that one I'm optimizing over y and x as a parameter. So they're coupled. I grab with respect to y of that thing, constraint stuff, multiply stuff, whatever, and stack it all up, and here's those optimality conditions. So what I'm going to do here is I'm going to take the optimality conditions for all the blocks. I'm going to stack them all up and sort of simultaneously set them all equal to 0 and simultaneously solve this entire problem jointly over x and y. The reason we do this is particularly, so this reasons about all the cross-coupling between these problems, but a really key idea here is that we're going to, remember we saw that little row in the interior point method that's smoothing everything? Generally, how you solve these problems is you take a Newton step, then crank down row a little bit, and take another step, right? If I were to solve all of these to convergence and crank the rows down, then the derivatives get super nasty and stiff. What I'm going to do here instead is I'm basically going to jointly solve them and crank the rows down for all of these problems together using kind of standard ideas from interior point methods. And what that means is that now in each step of this guy, the gradients are well conditioned, and I get like reasonable optimization steps. Yeah.
So are there any cases where the inverse doesn't exist in the implicit function?
So it turns we're actually not even using that here.
Okay.
That was kind of just to like illustrate the idea. I don't have to do it here. What I'm doing is, so there it was, this is the maybe more standard approach where I solve this thing to convergence, then use implicit function theorem, right? Actually, to use the implicit function theorem, I need to solve it to convergence, right? Because I have to have like optimality conditions equal 0 to do this.
Yeah.
Here, I'm not even doing it. So here, I'm stacking up all the optimality conditions. I'm taking I'm doing Newton on this whole thing. So I'm taking one giant Jacobian in this whole mess, and taking a Newton step on the whole thing all together, and then gradually cranking the rows down on all the problems done together.
So
that makes sense.
Let's imagine the case where you have a cloth and you
Yeah.
are twisting it so that you can turn it into a rope. So there are lots of contacts happening at the same time.
Hard.
So yeah, I mean, in those cases, you're going to get stuck in local minima, definitely, right?
So, okay, so there's like a few things to say about this. If you're just doing simulation, this gets back to like some of the stuff I was saying here. So it turns out if you're just doing simulation, we're ignoring this. Each one of these is relatively benign on its own. And where this sort of non-uniqueness sort of comes up in that context is in this block. Okay, so it turns out, this is like a very subtle thing, and I get myself in trouble all the time with like really pedantic people. So, but they're wrong and I'm right. So here's the deal. So that thing is this least action principle, which if you want to go look at it, again, it's like way back here. Right, so this thing. So it turns out this objective function, this is basically kinetic minus potential energy, right? So what does kinetic energy look like? It looks like basically a quadratic, right? It's like 1/2 mv squared.
Sure.
And in the generalized coordinates context, it's like v transpose m v kind of thing. Okay, if m were constant, that's convex, right? It's a convex, if n is full rank and constant, quadratic objective, this thing's strongly convex, life is good. In general, in generalized coordinates, it's m of q, right? It's a function of q, and that introduces potential non-convexity. But if things are benign, right, mass matrices are supposed to be positive. So the way to think about this is the mass matrix is the Hessian of this problem, and for something to be strongly convex, the Hessian needs to be globally positive definite, right?
Yeah.
Mass matrices always have to be positive definite if you don't do anything stupid about parameterizing your problem and choosing your coordinates. So it turns out this problem, this is where I get myself in trouble. I call this the least action principle, Hamilton's principle of least action. If you come up with very pedantic people who've read their classical dynamics textbook a few times and noticed this is, there's some footnote in there that says this is actually the stationary action, and that it's not necessarily a minimum. It turns out that is technically correct, but practically irrelevant. The reason is for sufficient, so there's cases where if you make the time here long, it can become a saddle point in weird quantum cases. And that's because m of q can vary enough over a long horizon. But if the time steps are short enough, this thing is strongly convex. So that hopefully, that was a very long-winded digression to explain, like, in the simulation context, just simulation, this thing really is strongly convex and has like good global optimum. It's very benign. That strictly depends on having short time steps in your simulator. And when I say short, I mean like, it doesn't have to be crazy short. And this is also tied up in other like ideas like Nyquist sampling, like what the frequencies are in the dynamics and all this other stuff. But the short version of the story is as long as you take reasonable time steps, the dynamic simulation stuff has unique solutions. It's benign.
Okay, thank you.
So if you took those KKT conditions, can you back out, excuse me, what the optimization problem it's actually solving would be? Like,
okay, so you're asking like what this weird optimization problem is with all this stuff stacked up. Yeah, so it turns out, we've done some work on this that I'll tease maybe later. This thing is an instance of what's called, wrong slide, this thing, with all these stacked optimality conditions. This is actually what's called a generalized Nash equilibrium, as in Nash from game theory. So this is a game theoretic
it's like a
equilibrium.
type.
It's not a minimax, right? Like, so that minimax thing, that's a Stackelberg game. So there's different notions of equilibrium in game theory. The minimax thing is Stackelberg.
Okay.
This is a slightly different thing. This is called a Nash equilibrium. What it is basically, if you imagine a bunch of players, it's like a stalemate where no player, the definition in the game theoretic context is that no player can unilaterally do better with respect to their cost or whatever by acting like unilaterally. So it's like where everyone's doing the best they can and kind of reaches this stalemate. That's the way to like interpret that in the game theory context. We've actually done some work on this like Nash game stuff as well, and it sort of came by, we were doing this anyway, and then I figured out at one point by talking to a colleague who actually did multi-agent stuff and game theory stuff, that this was a Nash game, and then we used our algorithms to go solve the Nash game problems. It was cool. So that's what it is. It's not, so the reason this is like maybe a bigger deal too is that you cannot solve this with it is not a classic optimization problem. Like this stacked, strongly coupled thing is not an optimization problem in the classical sense of minimize some objectives subject to some constraints. What it is I took a bunch of minimization problems where I'm minimizing with respect to maybe different variables and different constraints, and they're cross-coupled through where some variables are parameters of this one that are decision variables of this one, et cetera. And this is very flexible, right? I can like have stuff show up in the objective of this one that's from this one, or the constraints of this one and this one. But the whole idea here of like, kind of coupled optimality conditions that I solve jointly, this is exactly a Nash equilibrium.
Right. So that's like the best way of expressing what you're actually doing. Like,
yeah. Like if you want to think about it as, I don't know, that is the context, I guess, or like where this shows up in other places, and maybe like another way to think about it, yeah.
Okay, great. Thanks.
There's a question from online. Yeah. What are the implications of composing the KKT conditions compared to doing joint optimization where we optimize a cumulative cost that includes the cost of the individual subblocks?
So it turns out you can't do that in this context. So if you were like what that's talking about is maybe like summing the costs from each of them or something. There's lots of contexts in which that you do that sort of thing, like it's sometimes called multi-objective optimization. There though, the solutions you get depend on the relative weights of the, it's just like a different problem. Like that is not a good model of this situation, I guess. If that answers the question. Okay, so cool. So this is the idea. This is how we do it. Interior point method for all blocks, stack all the optimality conditions, and then solve it all together as one big, jointly coupled problem, also known as Nash game. Okay, so we've done a bunch of stuff with this. One thing we've done with this is build a simulator that has some cool stuff in it. Don't try to go run the code because it's a mess. I was talking about this earlier today. It's kind of abandonware, unfortunately, because the 2 PhD students graduated. But basically, what this is these subblocks, right? So if I take like impact dynamics, fuel friction, and the collision stuff, and I couple that together, I get a simulator. We did this. It's called Dojo. And cool things about this, compared to if people have done simulation and used, say, Mujoko or Bullet or any of these things, they all have various quirks. So in particular, a lot of them have interpenetration artifacts or soft contact stuff, which Mujoko, right? So we don't have any of that. Another common problem is creep. This is where you're not exactly satisfying stick slip from Coulomb friction. Mujoko also has this kind of thing where if you put something on an inclined plane, you'll always slip a little bit, and you can never get true sticking friction. So we fix that. As a fun sidebar, also it turns out that directly minimizing the least action thing automatically gives you good energy and momentum conservation properties. This is like not obvious, but it's cool. And then finally, taking advantage of that log barrier smoothing stuff, it can also give you smooth gradients to do whatever kind of optimization you want to on top of this. This sounds like having your cake and eating it too. Like you shouldn't be able to do this. I'm telling you, I can give you true hard contact with no artifacts, and I can give you gradients, right? Usually, this means non-differentiable. This means soft contact model. Can't do this, right? So how do we do this? The answer is, again, back to this like interior point sort of set of ideas. What I'm showing here are a couple of examples. The first one is like a block in contact with the ground around kind of impact or lifting it off the ground. And the second one is pushing the block sideways where you've got stick slip. In both cases, these are non-differentiable, right? So if I send the block to the ground, I get some step thingy that looks like that. And if I push the block sideways, I get stick slip that similarly looks like this. What these pink lines are me varying the rho in that interior plane method, that central path parameter, and showing you like the smoothing effect you get in the physics, right? This is impact smoothing, this is stick slip friction smoothing. And what you see here is as I crank on the rho, I asymptotically approach the true sort of step function answer. So what I can do here, which I think is kind of powerful, is I can simulate this, and I can crank rho all the way down when I evaluate the simulation step. But as I crank it all the way down and I converge to that hard contact answer, if I cache the last few solutions, I basically have access to all of these smooth versions for free. So essentially what we're doing is we're giving you the pose solution, the next time step states of the fully converged answer. But then when you query for the Jacobians or the gradients or whatever, I'm going to give you one of the cached values with a relaxed row. And I can pick which one I want, and I can tune this and do whatever I need. But it turns out essentially what we're giving you is the true hard contact solution, but then the smooth gradient. And lots to say about this. It turns out just empirically works super well for a lot of things. So I'll show you a few of those examples. First, a comment on this weak versus strong coupling thing though, just now that we're in physics land, to show you what this does, right? So this is showing strong coupling between kind of the collision checking stuff and the impact dynamic stuff. This is a little subtle and a little surprising. So if you do standard stuff that literally all simulators do now, which is you use GJK or something to find your closest points, your collisions, and you take those, so think about that as that's the weakly coupled answer. I solve the collision checking problem. If I'm lucky, I get the gradients too. I take the answer and the gradients and I plug them into my physics and I take a physics time step, right? If you do that, you get all kinds of weird artifacts like this. What's happening there is, okay, if I take two blocks and I put them face to face like this, what's the closest point between the blocks? It turns out that's a singular problem. It's ill-posed because it's literally any point on the two faces, right? But this is how all the simulators work. They have some geometric collision checker, and so what that's doing is, if I go plug that into my collision checker, what it'll probably spit out is something like the centroid of the contact patch. Seems perfectly reasonable. But when I go plug that into my physics and I take a time simulation step, that knows nothing about the mass distribution, anything like that. So I can't stack blocks, is the short answer. Because the collision checker doesn't know anything about the physics, and vice versa, right? What we do instead, when we do this strongly coupled thing and solve these jointly, effectively, so when the collision checking thing on these spaces, I need to regularize that somehow to get a solution, right? So if I put some kind of standard, I don't know, Tikhonov regularization, L1 regularization, whatever you want, you're going to get something like a centroid point. When I do this, what's happening instead is effectively the impact dynamics problem is regularizing the collision checking problem. And what the impact dynamics thing is, that's F equals ma stuff, that's the least action stuff. And what least action is doing is minimizing energy. So with this guy regularizing, with them coupled together, it turns out you get unique solutions to the closest point problem when they're coupled. And those solutions are the ones that minimize the action or minimize energy. And it turns out those naturally return the points at which these guys balance and stay still. So you get this really cool cross-coupled, sort of physics-informed regularizer effectively in the collision checking problem. And as a result, you get the right answer with the blocks balance for free. You don't have to do anything. You just stack all the physics up, stack all the geometry up, and it just happens. To my knowledge, no physics simulator currently available can solve this problem. And literally what they do, they introduce heuristic hacks all over the place to try to make that look reasonable. But the physics just isn't there. It can't do it at a basic level. Okay. So that's that strong versus weak coupling thing, why it matters. This is other stuff we've done, right? So you can do, let's see what's in here. The first one is just doing standard trajectory optimization stuff on a hopper. This is the half cheetah doing a policy gradient method. But we're doing analytic policy gradients here. We're literally just dipping through the whole stack and taking the actual gradients. We're just taking gradient steps rather than doing some weird sample, stochastic, SGD policy gradient thing. It turns out that's way more sample efficient, which is not surprising. This one is doing state parameter estimation. So we're flinging the block, and then we're actually trying to estimate the block geometry and mass and all that kind of stuff. And again, you can just diff through the whole thing and take gradients with respect to the parameters, the trajectory with respect to the parameters, you get parameter updates and kind of get stuff. And this last one is doing sample-based planning, RRT style planning, with a distance metric that's again informed by the gradients through here. It gives you good kind of manipulation planning stuff. So all kinds of stuff that you can use the gradients for, right? Kind of obviously, and get cool things to come out. Okay, so from there, now we're going to talk about putting the whole mess together. So this was, roughly speaking, Gojo, and then now we're going to do this on top of it, right? And in particular, we're going to try solving these kind of quadruped locomotion problems. And this is actually the top left one there is old work from when I was a postdoc. And the bottom one is recent stuff that we did on top of Dojo. Issue here is these take like these short trajectory snippets using kind of standard solver stuff on top of this. It's really expensive. It takes minutes to solve for these like very short little snippets. And ultimately, we want to be able to do this stuff in real time. So now I'm going to show you like how we got this to run in real time on some robots, which is work we did last year that just got, actually finally just got published in TRO like last week or something, if you want to see that. So here's what we do. Like, so take this mess. All these are, relatively benign, but like nonlinear and expensive to solve, blah, blah, blah. So ask the question of like, what can we approximate in here while still maintaining the overall flavor of this, and in particular, still maintaining the ability to reason about contact events, the ability to like understand, how to make a great contact with the environment and not bake that in. So what we're going to do here is sort of try to formulate an MPC, kind of an online model driven control problem from this, using relatively standard ideas. So what we're going to do is like, say we solve this offline and we get a gate. And what we're going to try to do now is track the gate rather than solve that from scratch. So in our optimal control problem, we're going to replace like the cost function there with a very simple quadratic tracking cost. Exactly the sort of thing you're used to seeing in model driven control. So that's super benign now. It's just trying to track some reference gate, say, on the quadruped. Next, we're going to go inside this dynamics block, and we're going to linearize the manipulator dynamics, the robot rigid body dynamics. When I mean there in particular is that problem, right? The original problem is that least constrained least action thing. We're going to just linearize. We're not going to linearize the contact stuff in any way there. We're going to keep those constraints there. We're going to linearize the dynamics of the robot, though, just the rigid body dynamics about that reference gate motion, right? Sort of standard stuff. And then in this kind of collision block, what we're going to do is, similarly, we're going to linearize the sign distance function about the reference. Okay, so like one way to think about it is we're linearizing bits and pieces inside all the blocks. So we're making each one of these optimization problems in each block a simpler, easier to solve optimization problem, but we're keeping the overall structure, right? And then lastly, again, for kind of speed reasons, we're going to go and linearize this friction cone in this guy. We're going to approximate it as a pyramid, which is a very standard thing to do. Yeah?
Each one of these blocks then has an optimization problem that's optimizing with respect to its own variable,
yeah,
but then is parameterized on blocks.
And
the arrows are denoting the coupling.
The coupling, exactly, yeah.
Just wanted to clarify.
You got it.
Thanks.
Okay, so this is like all the approximating we're doing. So we're keeping that like Nash equilibrium stacked optimality conditions set up. We're just going in and approximating the individual problems to make them nicer. So in particular, with this approximation, this becomes like an LP, this is an LP, this is an LP, that's a QP now. And then this thing up top is like, it's got a quadratic, nice, clean objective, but it's constrained by the solutions of those. It's still a little weird. It's definitely, the whole thing is nasty, but we've made all the pieces a lot nicer, right? And easier to solve. Okay, so we did this with all these approximations and frankly, like a heroic level of implementation engineering by a couple of my PhD students. We managed to get this stuff to work at like reasonable real-time rates. I'll show you some of that now. First, some like simulation teasers. So we call this PunchBot. It's an inverted pendulum, and it has this like kind of ball on an arm kind of thing on top. It's like the model is a ball on a prismatic actuator that can go side to side. So this thing has a mass, and it can use that ball to balance. But it can also reach out and touch the walls. So this is basically the closest thing to like convex MPC in this context you can get. Literally what we did is linearize the inverted pendulum about that upright equilibrium pose, and then linearize the sign distance functions. So it has all the information, but everything's linearized. There's no pre-specified contact in there anywhere. It just has the sign distance function, between the walls like this. Everything's linearized in the way I just described, and we just solve that MPC problem online at like 30, 40 hertz. And if I knock the thing, it knows it, just kind of emergent out of the solutions to that MPC problem. It knows that it can reach out and push against the walls when it needs to balance. Again, no pre-planned contact modes, no heuristics. It's just the problem that I just showed you. Kind of fun, like again, it can discover new contact modes online, basically, right? This is one of my favorite simulation results. So to me, this is wild, and was like the thing that convinced me that this was like gonna work and gonna be cool. What you're seeing here, this is a simplified quadruped model. We call this the point foot model. So it's a single rigid body for the body and then point masses for the feet. And actually, funny enough, has the same number of degrees of freedom of a full quadruped model with all the joints and stuff, but it's just like simpler to solve. Anyway, what you're seeing here is we took this guy, we gave it a simple trotting gait, standing still at the origin and trotting in place. That's the reference motion that we linearized about. That's it. So it's linearized about this trot in place motion, linearize the sign distance function about that. It's just periodic reference, linearize the rigid body dynamics, blah, 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 the whole thing. And then we just kick the crap out of it at the beginning of this simulation. It's flying through the air, flailing around. It's figuring out like if you think about how this is classically done in these robot controllers, there's like a mess of, there's literally an entire literature on push recovery for legged robots, filled with heuristics like capture points and like where to stick your foot out to like catch your fall. None of that. This is just this, all it is this stock periodic gait reference that I linearize everything up. I kick it, it flies through the air, flails around, figures out how to catch its fall, land on its feet, and then trot back to the origin, back to its like reference pose. All with all that problem I just shared with everything linearized in all those places and approximated. So I think this is amazing, very frankly, having like that modular stuff in it. The fact that it doesn't need any of those like outer loop, foot step planning, like push recovery heuristics or anything. It's all just falling out of that problem in like a supernatural way. Okay, so that's simulation step. We have stuck this stuff on real robots. This is that controller I just showed you in Sim, like running on these little industry quadrupeds. It is obviously not as good as state-of-the-art controllers that you've seen, right? Like, and I think a big part of that is that this controller is running at like, I don't know, 30 or 40 hertz. It's running really slow because it's super hard to solve those problems, and frankly, because our implementation, like, to solve these things, we have to write our own like crazy sparse linear algebra kernels and like all kinds of very hardcore low-level numerical optimization stuff. And it was like a couple of PhD students just getting it to be good enough to run at real time. And so I think there's a ton more work that could be done to make this go a lot faster. I think the main reason it's like, it's working, but it's not as reactive and responsive and fast as like state-of-the-art FTC controllers. Because those are running, frankly, at several hundred hertz. This is only running at 30, 40 hertz on this guy, which is really slow for these. It's just barely fast enough to actually work on hardware and stabilize it. Okay, you can do this obviously much better with a hybrid, kind of like standard FTC approach, but stuff that we're currently doing, that stay tuned for hopefully some submission to ICRA in the fall. This is a summer project. You can, leveraging all the stuff I showed you, so that trotting controller, all it knows about are point contacts on the feet. It doesn't have any knowledge or any information about contacts with the rest of the body. But the setup that I just showed you, right? We have all this, nice collision checking stuff. I can reason about arbitrary contacts anywhere on the body, and so I can use the head. I can lean over onto things, and it's just all in there. It's all very natural. It can do all kinds of weird stuff. So this is just like a very dumb. This is like the first thing try, but like trying to get at stuff where you're leveraging those other contacts, right? And like contact-rich behaviors where I can make contact with the knees, with the head, with the rest of the body, and also deal with not just the floor, right? Like more complicated environment geometry. So we have some very fun demos coming soon, hopefully, to work on right now, along these lines of weird, more complicated contacts. And I won't say any more about that. I don't want to keep the fun punchline away. Okay, so yeah, stay tuned on that. Hopefully this summer, in the fall, do some cool stuff. Some other stuff, so finally to finish off, we went through this whole mess of stuff. I want to mention a handful of other, I really focused on this whole contact and simulation and legged robot story, but other stuff that this composable optimization thing is relevant to, and I think is a pretty broad idea. And some of these will come up already. The first one that we've actually done, the thing on the left there, maybe I'll let that start over again. This is a highway merging thing with cars. We've used the same stuff to do online Nash equilibrium MPC. So this is game theoretic MPC, where you're reasoning about the behaviors of the other agents around you and how your actions couple into theirs. In particular, does anyone know about the frozen robot problem in driving? Yeah, so the idea is if you're merging on the highway and there's not a gap big enough for you to squeeze in, what a lot of current autonomy stacks do will just slam the brakes and sit there and say, I can't safely merge, right? Because I can't satisfy my no collision constraint. But what we do in that scenario is we kind of nudge our way in there and assume, based on prior models of the other drivers, that they also don't want to hit us, and they're going to kind of make room for us if we're kind of aggressive and nudge our way in there. And if you set that up the right way, basically what we're doing here is we're making assumptions about the other drivers, in particular in this context, assuming they're all solving a similar MPC problem to us, with similar collision constraints and similar objectives. And if you do the same block thing like that and solve it all jointly, you get stuff like this, where you get like legit highly emergent behaviors. You can reason about the cross-coupling of, so game theoretic, kind of multi-agent, like adversarial or non-cooperative multi-agent interactions. Super natural to do in this coupled kind of composable optimization context. I mean, that's where it comes from actually originally, is this Nash equilibrium idea. Other stuff, this is some examples of robust control stuff, like you mentioned before, like the minimax kind of stuff. Also super natural to throw in this context where you're like, this is like a sort of cartoony SpaceX rocket landing example where you've got fluid slosh in the rocket, and we've like optimized a robust controller here that's like got some bounds on what that sloshing can do, and is solving this kind of minimax problem to get like a safe landing to happen in spite of uncertain slosh dynamics, essentially. And we simulate this with the truth model. So that stuff, there's like lots of other applications in game theory, robust control, all kinds of other stuff for this composable optimization stuff is relevant, kind of interesting. Another big thing we're working on right now, this just got submitted to ICRA camera rate, is trying to solve these things faster. I mentioned like it's super hard to solve these problems. We're doing that on, ultimately the stuff I showed you was all on a single CPU core. It's parallelizing is hard, blah, blah, blah. We really want to be able to take advantage of parallelism of GPUs and to solve these largest problems a lot faster. And part of that effort is just trying to solve, as a starting point, solve QPs on the GPU. This is a paper called Lulu QP, just a fun advertisement, I guess. And the idea here is that we figured out a way to reformulate an ADMM solver. So if you guys are familiar with OSQP, it's based on the OSQP kind of algorithm. We figured out a way to turn that exactly analytically into a deep weight-tied rating network in closed form, and then you throw it at PyTorch and throw it on the GPU and get like dramatically faster solve time. So this is doing Atlas in that demo at like 2.5 kilohertz, the full body model with all the torques and everything, which is wild, and like an order of magnitude faster than the fastest like CPU-based solvers. So that's kind of cool. And then, yeah, we're also kind of getting into manipulation-y stuff. This is, again, very similar stuff to what I just showed you. This is actually the collision stuff. But what's going on here is the idea is that, you know, classically when you do these like LCP methods or whatever, you have to like, it's standard to like use point contacts on the robot with the environment or something. And the idea here is I know the robot geometry really well a priori, so I can go do that convex decomposition of the robot body very easily into like pills and capsules and boxes and whatever, and here's the grippers basically. The environment though, I don't know a priori, and so using convex decomposition on the environment may be a bad idea. So here what we're doing is like modeling the environment geometry as a point cloud, and we're explicitly using the point cloud here to do all of the contact calculations, force calculations, etc., to like, you know, grasp the bunny and whatever you can imagine. The idea here is that like you could use raw point cloud data from, you know, a LiDAR or something and just throw it into your simulator or your MPC thing and like kind of reason over it very directly. Kind of cool. And yeah, we've also got some state estimation stuff that's cool. That's like trying to reason better about contacts and foot slip, stuff like that. This is actually about to go into TRO. Care about that. And then yeah, this stuff. I don't know. The idea here is like, I guess you could call this like real to sim or data-driven simulation. Like this Dojo thing is fully differentiable, and we've done a little bit of kind of teaser society stuff. But the dream here is to be able to take data from the real robot and look at the model mismatch, and then feed it back into the simulator and actually say improve the geometry, actuator compliance stuff, friction stuff, all the messy stuff that's hard to model with a classical rigid body model, to like try to estimate that stuff and use this idea and pull it back into the simulator so that maybe next time you don't have to do transfer learning or whatever, right? And again, the differentiability here helps you. And in principle, in all these places, you can strategically bury like function approximators, whatever you want, right, to try that stuff. Okay, I will shut up now. I think I've like gone a little over time, sorry. And yeah, also a bunch of these awesome people did all the hard stuff. And this is how you get hold.
All right. Awesome. Who has a question?
Yeah, great talk. I do some similar work. I do object placement planning using optimization, and also my approach is physics-based. One really big problem I have is to know where are the contact points for contact edge manipulation. With the Stanford bunny you showed, there was two little animations, and both bunny did drastically different.
Yeah, okay.
The outcome was really different, although initially the robot was pretty much in the same pose.
Yeah, let's see if I can play this again.
Yeah, so one is rotating
Yeah.
and the other is not, right?
Yes.
And so this is because the contact points are not exactly at the same place.
Yeah, so this was a workshop paper from IROS, and I didn't tell you what was going on here, and I just threw the video in because I was lazy. Sorry. I was
Yeah,
rushing to
so
get I'll tell you what's going
I
on.
find like, okay, so in the rest of your presentation, spheres are used for like toes,
Yeah.
and even in like small toy problems, because spheres are nice, it's basically a single contact point, we know where it is, we can model the reaction forces really easily.
Yeah.
Now with the Stanford bunny, it's very different, right?
Yeah,
You don't
exactly.
know, plus it's probably some kind of soft
It's a
contact
little bit
going on.
compliant. Yeah.
So,
So let me
what's-
explain what's going on here.
I want to know how you would approach the problem of dealing with dealing with not knowing where the contact points are.
Yeah. So this is a fantastic question. Like, yeah, there's always geometric uncertainty in these things, right? And like one of the arguments I hear a lot for like soft contact models, like on the Joko, is that, oh well, rigid body is an approximation and everything's really a little bit confined. And this is actually very much embracing that idea. So what this is, the one on the left is a standard point contact thing. And one of the things that happens there is obviously like you're gripping 2 points, there's no torsional friction or whatever, and whatever. The thing on the right, this is the exact same point cloud, same everything. But what the thing on the right is doing is it's called a soft finger model in the manipulation community. You're familiar with this? So what it's really doing, it's a kind of like first order approximation of a slightly deformable object or slightly deformable gripper. Basically what you do is you endow all of the contact points with torsional friction, which corresponds to them basically being small patch contacts, right? So that's what's going on there. So we can do that stuff. I'd say like, I don't know that I have like a super good solution to this problem in general, but like, I do kind of think patch contacts are important. We should be thinking about this more. This is like our attempt at getting at some patch contact stuff in an easy way that easily kind of slaps into our existing framework without having to change too much. We have thought a lot about in the collision checking thing with all this convex primitive stuff, like how to actually reason about face-to-face contacts in a rigorous way. I can tell you some of the things we've talked about but haven't done yet. This was the easiest thing to do, so this is what we did first. But some of the things we're thinking about doing is when you have that face-to-face contact problem, a cool idea that again we haven't implemented yet, so this is like kind of speculative and dumb maybe, but when you do this, you can actually use the Jacobians to kind of back out sort of like a rough proxy for a patch. Like basically you can imagine I can take this kind of like Jacobian thing and kind of think about like turning that into kind of an ellipsoid that corresponds to the patch. And based on like the eigenvalues and eigenvectors of that thing, I get effectively like a patch size and a patch, like for an ellipsoidal patch basically. So we've thought a bunch about how you might exploit that to like get at patch contacts in like some kind of reasonable way. I totally agree with you. Point contacts are like kind of a very bad like first order approximation of reality. And I think it really depends on like how compliant your stuff is. I think this soft finger model works reasonably for like relatively rigid but realistic things. And then as far as patch contacts go, I think the best work I'm aware of is the like hydroelastic contact model in Drake. I think that's like a very cool idea that really gets at patch contacts in a pretty nice way. The downside is it's super expensive to evaluate, right? They're basically having to compute like volume integrals at the intersection of these bodies. So it's really expensive to do the volume integrals, and then it's also really expensive to do the simulation the way they're doing it. They're basically formulating this in continuous time with forces that are proportional to volume intersection, and then they get really stiff ODEs, and they have to use a very fancy stiff integrator to simulate. So I think because of all that, it's like kind of expensive, and it's really good if you care about super precise simulation, but I think it's probably not the right thing to have in a control loop, like a model predictive controller. It's too expensive for that. So I don't know. I think it's very, very, very context dependent.
Thank you very much.
Okay, I actually have 2 questions. Sorry. My out there question will ask first because it's related to this.
Okay.
Is there, so you said, obviously in reality, every rigid body has some compliance. Is there some relationship between the amount of that compliance and the row in the method?
No.
No.
No. So
Because intuitively it seems like,
yeah, so okay, that is getting at the difference between a barrier method and a penalty method. So you can think of like a lot of the current soft contact models, they're kind of all doing like, they don't typically think about this, but they're all kind of, at the end of the day, kind of doing similar things here, but they're not explicitly setting up as this like coupled optimization. They're making approximations such that they can like kind of collapse all those problems down, maybe. But yeah, a lot of those cases, particularly in Mujoko, and also any kind of like nonlinear spring damper model, like really all the soft contact models, they come down to, if I took my optimization formulation there, and instead of the barrier on the interpenetration constraint, I used a penalty method, which penalized interpenetration. So barrier methods blow up to infinity at the constraint boundary. And the reason they're called interior point methods is they strictly guarantee that the iterates are always in the feasible region. So said another way, if I solve that thing with an interior point method the right way, I'm guaranteed to never have penetration at any time, any of the iterates, right? And the way to think about that, what that log barrier is really doing is giving you like kind of a force field away from the surface, such that you're always going to stop before you actually touch the surface. And you actually only land on the surface in the limit of rho getting cranked all the way down, right? A penalty method instead, like naively, you could take the constraint and like, square it and put it in the objective function, right?
you could do one more thing though. You could add a slack variable, right? And then you could design a penalty that also gives that guarantee of, if possible, landing inside.
So there's, okay, let me maybe get back to that. There's like lots to parse there. This might be a longer conversation. But basically, if you were to use something like a quadratic penalty, that would directly correspond to like some kind of spring damper model, where it's allowing some interpenetration, but then giving like some kind of restoring force. This is what happens in Mujoko or like a bunch of these other simulators, right? So that's like what's called an exterior penalty versus an interior point method or barrier method, right? And it comes down to the algorithm, in the interior point barrier case, cannot allow interpenetration by construction, whereas a barrier method that kind of embraces interpenetration as part of the algorithm and like gives you a way of computing the way out, right? So what you're talking about, the slack variable, is a good idea. In fact, we do this because in a lot of cases, like if you're doing state estimation, for instance, it's really hard to guarantee feasibility. Like if I'm trying to do state estimation and I like have this random noisy thing, and then I try to take that and plug it into my simulator, it's very possible to get infeasible states that have a little bit of interpenetration given noisy measurements. And this will barf, make the thing barf, right? So if you know a lot about interior point methods, you may be familiar with infeasible start interior point methods, which if you go read the textbooks, like all modern interior points almost do this. And what that does is exactly what you said. It introduces slack variables that, and you impose the constraints on the slacks. And then you have equality constraints setting the slacks equal to the real stuff. And what that lets you do is have an infeasible initial guess that doesn't have to strictly satisfy the constraints. So you're totally right. I glossed over that a little bit. We are doing that, and it helps a lot in practice. And I guess, practically speaking, that is introducing some kind of restoring force type thing, but the difference is that we solve these things to convergence, every time. So we're basically always iterating the slack stuff out. After a couple of iterations, it's always strictly feasible. The solutions are always in the feasible region.
And sorry, and the second question, sorry, I'm being selfish. For the MPC that you presented, you said you were linearizing around the reference trajectory. Is there anything that anecdotally you had to do to the reference trajectory to make sure your linearization didn't break?
So no, although you almost certainly will there's always caveats to stuff. This stuff is actually surprisingly clean. Honestly, there's very few hacks. There's tons of hacks in the implementation, to get this to go fast. We did insane stuff, that I won't get into here. It's ridiculous, but yeah, surprisingly good. And I think, honestly, this is the demo that really convinced me of this. And at the end of the day, what we're trying to do here, as a classical control guy who likes convex things or whatever, convex MPC is insanely good. Like linear models are insanely good if you like kind of respect where they are valid and stuff like this. Like, I don't know, I teach a class on this stuff, and I love the classic Art Bryson quote, like, be wise, linearize. Like, it's true. Like, you can make insane things happen with convex NPC. Like, we got drones going and doing aerobatics and crazy stuff. It's super, super good, right? If you know how to do it. Like the linear models are super powerful. And I think lots to say about that. One take on that is the models are all approximate anyway. So if you can get away with a linear model, you should. And so that's kind of, I think, really borne out here. There's everything in here is locally linearized. We're keeping the overall structure, but we're solving LPs and QPs in each of those blocks for speed reasons, and it's insanely good. It can do crazy stuff that I would never imagine, right? Like fly through the air, reason about push recovery, trot back to where it's supposed. All of that just comes out with free. We didn't do anything, weird or heuristic there. So,
thank you very much.
Anyone else have a question? So I have one. So since you mentioned that everything is optimization and you put state estimation in there, do you think perception with neural networks should be part of this pipeline where you
100%,
optimize features? Yeah.
Yeah, we're trying to do this now.
Yeah.
So
does it fit in the same story with a natural equilibrium type of formulation?
You can, yeah. I guess this work is doing, we're doing visual inertia stuff. We're also doing we're doing a bunch of kind of vision in the loop, pose estimation stuff. And what we're doing is pretty standard, I would say. We use a vision network to do landmark classification or whatever, and we take those vectors and feed them into a more or less classical. We basically treat the vision network as a sensor input to a classical state estimator. That said, I think there's tons of good stuff to do even there, where you're decomposing it and treating it as some stack with some pieces that are neural networks and some pieces that have physics models. That's kind of what's going on here. What I think is really interesting about this is given this whole differentiable pipeline, we can train that end to end. We can actually train on the end covariance and pose that's coming out of the estimator, where we write down the estimator with the dynamics model setting and take gradients through the whole thing and use that in the neural network training. So I think our students kind of getting into that now. We're poking around in there. But I think there's it definitely fits into the story. And I think this, there's also lots of other work on complex layers and all this stuff. So this idea of diffing through optimization problems and embedding them in learning algorithms, I think is not novel, right? And it absolutely fits.
Sure, but compared to methods that would apply something like expectation maximization for these types of
Yeah.
would you prefer having end-to-end optimization, like the philosophy you're saying here, or having type of EM where you separate these?
Yeah, that's an interesting question. We've done both, and I wouldn't say that I have a super strong take on that at this point. Yeah, still thinking about that one.
Gotcha.
There's one question from online.
Yeah.
A student is asking, what's the best environment to create a high-fidelity robotics dynamic simulation with flexible bodies? They said that they've thought about Craig Benton and reduced modal representation.
I do not have a good answer for this. It's the Wild West.
Okay, that's it.
Okay. All right, any more questions? Last chance. All right, maybe let's land the plane here, and thanks, Zach, for an amazing talk.
Yeah, thanks everybody. Thanks for
Cool. All right.